Good evening and welcome to Physics News Network. Today we investigate the motion of Atwood's machine, a classic physics system used to study acceleration, force, and tension. Our team conducted two experiments, a single pulley system and a more complex double pulley system. Our goal was to compare theoretical predictions with real-world experimental data and analyze any discrepancies. Let's go live to our field reporter for a closer look at the setup.
Thanks. Let me go over the equipment that we use for this experiment. So as you can see here, we used this Atwood's machine setup consisting of a pulley system, some string, mass holders, and calibrated masses. Additional equipment included a motion sensor connected to a computer using Pasco Capstone software to record velocity over time. For part 1, we used two masses, 205 grams and 105 grams. The heavier mass was released from a higher position, causing the system to accelerate. For part 2, we introduced a second pulley to analyze a more complex system using masses of 200 grams and 75 grams. The motion of the system was recorded and analyzed using velocity versus time graphs. And now back to the studio for you.
Thank you. To understand how the system should behave under ideal conditions, we turn to our data scientists for theoretical calculations.
So, in the beginning of our data collection, we ran into a few hiccups. We couldn't get the ropes to stay on the pulleys because we hadn't done anything like this before, and we really kind of just lacked the experience of working with this the Atwood machine. And it took a few tries for it to actually stay on, and so we can accurately measure it. And then the second problem that we had ran into was that the computer it was not being at all helpful at all this day. It kept freezing, leading to incomplete data or no data collection at all. And so it made us work faster in the time kind of leading up to when it would freeze. So we were rushing a bit to collect the data, such as putting up the right, like highlighting the right area so we can get like the right numbers that we needed. And this kind of um, forced us to work faster and to kind of accept whatever data we could get because in between each um, data collection, we would have to reset the computer, which would take anywhere from 5 to 10 minutes depending on what it had to do. And this really did slow us down.
For the single pulley system, we use the equation acceleration is equal to m1 minus m2 over m1 plus m2 times gravity. Substituting our values, m1 is equal to 0.205 kilograms and m2 is equal to 0.105 kilograms. We calculated a theoretical acceleration of 3.16 meters per second squared. From our experimental data, we measure an acceleration of 3.00 meters per second squared. Using the percent error formula, percent error equals 3.00 minus 3.16 over 3.16 times 100. We obtain a percent error of 5.06%, indicating a strong agreement between theory and experiment.
Those results show impressive accuracy, but what happens when the system becomes more complex? Let's take a look at the double pulley system.
For the two pulley systems, the equation changes to A equals m1 minus 2m2 over m1 plus 2m2 times gravity. Using m1 equals 0.2 kilograms and m2 equals 0.075 kilograms, we calculated a theoretical acceleration of 1.440 meters per second squared. Initially, the graph produced a slope of 7.89, but this was identified as a transient spike caused by the release of the system. Instead, we analyzed a stable linear region of the graph and calculated an experimental acceleration of approximately 4.17 meters per second squared. Using this value, the percent error was calculated as 4, 4.17 minus 1.40 over 1.40 times 100, which gave us a 198% error.
So what caused the differences between theory and experiment? Our team identified several contributing factors.
This large error is expected due to increased friction, additional pulley interactions, and the limitation of the theoretical model.
So, for the real world example, imagine a construction site with a tall crane lifting a heavy load. This crane works like an Atwood machine. On one side, you have the load being lifted, like a bundle of steel beams, or in this case, a concrete block. And then on the other side, there's a counterweight attached to the crane. Both are connected by a cable that runs over a pulley at the top. In physics terms, the load is one mass and the counterweight is the second mass. The pulley allows them to move in opposite directions. If the load is heavier than the counterweight, it will move upward, and the counterweights will rise. If the counterweight is heavier, it helps lift the load upward with less effort from the motor. This setup is useful because it reduces how much force the crane's motor needs to use. Instead of lifting the entire weight, the motor only has to handle the difference between the two masses. So just like the Atwood's machine, the motion depends on the difference in mass, gravity, and the tension in the cable. In real life, cranes also have friction and powerful motors, but the basic idea is the same. Two masses connected over a pulley, balancing and moving against each other.
In conclusion, our investigation demonstrates that while theoretical models provide strong predictions, real-world systems introduce variables that affect accuracy. The single pulley system showed excellent agreement with theory, while the double pulley system highlighted the impact of complexity and friction. This experiment reinforces the importance of understanding both ideal physics models and real-world limitations. Reporting live from Physics News Network, thank you for watching.
Percent error in this experiment primarily comes from friction in the pulley system, air resistance, and measurement uncertainty. The theoretical equations assume ideal conditions, meaning no friction or energy loss, which in this case is not realistic in practical setups. Additional factors include string mass, pulley misalignment, and inconsistent release of the masses. These factors are significant, especially in the two-pulley system, where complexity is increasing. To minimize error, we could use low-friction pulleys, ensure proper alignment, and increase mass differences, and collect data over longer distances. The percent errors are not equal between trials because experimental conditions vary slightly each time, affecting the results. So, before we even conducted the experiment, the expectations for what was to happen was kind of like what we had been compared to previously, which is an elevator. And I kind of expected that the weights would kind of balance out or at least go down at a slower rate than what we saw. What we saw was they moved really fast and they gave us almost no time to react, and it was just a big difference from what I would have expected to happen. So, in conclusion, this experiment shows that even a simple system like the Atwood's machine can explain how real-world cranes lift heavy loads efficiently, and it supports Newton's second law by demonstrating that acceleration depends on the net force created by the difference in mass.